Hi. So far in this chapter, we have focused on the distance domain. In particular, we focused on computing energy based on a force being exerted over a distance at an angle. And so the work that we have generated is force times distance times the cosine of the angle between. We would like to now connect this back to our previous work by considering the time domain one more time. And in particular, we'd like to answer this question: how quickly is energy added to or removed from a system? And this quantity, the rate at which energy is added to or removed from the system, we're going to call power. And the symbol for power is capital P, and we're going to compute that, as said above, as the rate at which work is done on the system. Now, of course, our work energy theorem tells us that work is equal to the change in kinetic energy. So one way that we could compute that power also is to look at the rate at which the kinetic energy of the system is changing. These two equations mean exactly the same thing, but one of them is measured from the perspective of the object supplying the power. So for example, if I have an engine or a motor, and it supplies work W in time delta T, then we could measure its power by saying how much work did you do in a given number, a given amount of time, and then we would get the power by dividing both by time. You can see when we do that the power that we get is measured in joules per second, and 1 joule per second is a watt. You've probably heard of watts before. For example, light bulbs are measured in terms of watts. If, on the other hand, I want to look at my system and ask how much power that it is receiving, then I would look at how quickly the kinetic energy of that system is changing. So this is really a retrospective way of measuring the power supplied to the system. And here the system receives energy and turns that into kinetic energy. So we can measure the power that a system is receiving by looking at how the kinetic energy of its components are changing. Now, if we have very large amounts of power, then we might measure them in terms of horsepower. And 1 horsepower is a very old unit, and literally referred to the amount of power that average power that a draft horse could generate if it was hooked up to a grinding wheel. And 1 horsepower is going to be 746 watts, or about 3/4 of a kilowatt. Now, the thing that we can do here is to be a little bit clever with our formula to get a third way to measure power. If I take work over delta T, and I write work as force times distance, and I rewrite the distance traveled as delta x, assuming that we are moving in one direction and not doubling back on ourselves or anything, then what I get is F times delta x over delta t. Delta x over delta t is the same as the velocity. So we end up with 3 different ways to measure power. And those are work over time, which looks at the object supplying power, or the change in kinetic energy of the system over time, or the force exerted times the velocity. And all 3 of these are useful in different contexts. What I'd like to do now is to share with you two fairly simple problems that illustrate the measurement of power. And the first one is in your book, chapter 6, problem number 64. How much work can a 3 horsepower motor do in 1 hour? So our situation here is that we have a motor. I'll just represent the motor as M, and that motor is supplying 3 horsepower. Now, we want to think of that as an ongoing process here. So notice that it occurs over a period of 1 hour. So the idea is we turn on the motor, that motor is a 3 horsepower motor, and it's going to run for a whole hour. And at the end of it, we ask how much work did that motor do? So there will be continual work being done as the motor runs. And the horsepower measures the rate at which that work is delivered. Here, because we're asking about total work, it makes sense to set power equal to work over delta T. The only tricky part is that I need to make my units work out. So we're going to have 3 horsepower, and we're going to convert that into joules per second or watts at the rate of 746 watts per horsepower. Notice that I write out the unit watts so that you don't confuse it with work. Eventually, I'll just write it as a W. But for now, as you're still getting used to it, I'll write out the word watts. And so that turns out to be 2,238 watts of power, about 2 kilowatts of power. And the delta T that we're talking about is 1 hour, but of course we're going to need to think about that in terms of seconds. We now plug all of this in. We have 2,238 watts equals the amount of work done over 3,600 seconds. And that turns out to be a very large number of joules. Or 8.1 times 10 to the 6th joules. Notice that a watt times a second. Excuse me, let me write it out. A watt times a second is equal to a joule. Very often you will see kilowatt hours, or the total amount of energy. A kilowatt hour literally means a kilowatt times an hour. And that's going to be equal to 1,000 joules per second, or 1,000 watts, times 3,600 seconds, which is 3.6 million joules worth of energy. And what's crazy is that 3.6 times 10 to the 6 joules a kilowatt hour of energy costs you only about between 10 and 20 cents out of the wall. So this gives you a sense of how to use power to measure work. Let's consider a second problem. And that second problem would be problem number 59 from chapter 6. If a car generates 18 horsepower while traveling at a steady rate of 88 kilometers per hour, what must be the average force exerted on the car due to friction and air resistance? So here we have a car, and our car is traveling down the road at 88 kilometers per hour. And that car is going to experience 2 different forces propelling it forward. 2 different forces, excuse me. One is going to be the force from the road as the tires push off the road, and that's a force of friction. And the other is that it's going to experience a force of air resistance, which I'm going to label Fr. And apparently these 2 forces exactly cancel each other because the speed of the car is constant. So if the speed of the car is constant and it's traveling in a straight line, then that implies that the acceleration is 0, so that the net force on the car is 0, or the friction cancels the resistive force. Now, where does that leave us? Well, first of all, I probably want to write that 88 kilometers per hour in terms of meters per second. So we do a little bit of converting. 1,000 meters an hour, 3,600 seconds. And so that gives us 24.4 meters per second. And second, we recognize that, let's see here, what else do we give? Yes, that the power that's generated is 18 horsepower. And so we're going to want to write that in terms of watts. And remember that 1 horsepower is the same as 746 watts. Which is 13,246 watts. Okay, and here's how we put it all together. For this, we know the speed, and what we're looking for is force. And so that suggests that we want to use the third equation from back here, which is that the power is equal to the force times the speed, or the velocity. Try that again. There we go. And so we set power equal to, here's our power in watts right here, we set that equal to force times speed, and the speed that we have is 24.4 meters per second. Do a little bit of dividing. And we get that the force is equal to 550 newtons, which is about the weight of a 120-pound person. So the conclusion is that in order for the car to keep going at a constant speed, the motor is going to have to be generating enough horsepower so that the force of friction can be 550 newtons to oppose the resistive force of 550 newtons here. And in particular, here's what happens with the car, and that is that as the car goes faster and faster, the amount of force that the car needs to generate just in order to go at a constant speed is going to increase. And actually it's going to increase at an increasing rate. This is going to put a cap on how fast any car can go because it is not going to be able to generate enough force to overcome air resistance at some point. So if you've ever wondered why you can't just push on the gas and accelerate out to an infinite speed, or even to the speed of light, it is because air resistance requires a certain amount of power to generate a force to overcome that air resistance and keep the speed.